like to welcome you to the second laboratory activity, bodies in free fall. Today's activity is pretty straightforward because we're going to be basically looking at something falling, just letting it go and dropping it. But before we do that, let's take a quick moment and look at this week's PreLab activity. James, catch. Thanks, James. Appreciate it. So, now, we're up here on the ladder in the PreLab activity. Now, I'm choosing a ladder because I want to be able to illustrate a good drop, but you can drop it just from arm's height, a little bit above, and maybe drop onto a bed or onto a pillow of some sort. So what we'll do is we'll get rid of this for now, and we'll take our data, we'll push play, it's going to begin, and you want to move kind of slowly so you can distinguish your motions out. And you want to do your very best to just drop it and let it fall right into your safe catching area. That's it. Now you zoom in, as we're about to see. When you first open up the Firefox app, you're going to see a whole list of experiments that run down in the orange area. We're looking for acceleration without G. In other words, there's electronics in the phone that will sense changes of motion, and what this one does it subtracts 9.8, so it gives a live actual acceleration as you drop it. So you click on that, you go into your experiment, and then you press play button, which is to begin the experiment collection. You have the trash can for throwing out the data. You can click on these three buttons here. They give you a few more options. You can look at experiment info, export data if you wanted to explore it in Excel or some other spreadsheet software. Say if you take data, you want to save experimental state, you will save it, and when you go back to the main screen, it'll show up as a blue file. You push play, and you can see that it starts to collect data. And you can see if you make certain changes, you can see that if I move it along the x-axis, that's where the clear transition's for, and there may have been a little bit of rupture on the other two, but clearly it was along the x-axis. If I go to Z, see the Z-axis is coming out of the phone, so this is the one that you see down at the bottom coming out large, and then Y, which is vertical this way. You see the Y-axis is now showing clear supplement or clear data compared to the other three. If you've already collected the data, however, what you have to do is just go back to your main screen. We're going to leave. And we'll go down and look for the experiment that you've taken, that you've given a name to. So we'll click on freefall. That's the data I took just a few moments ago. And you can see that there's very large spikes, which seems like that's where the important information is. But remember, the way I dropped it was along the z-axis. So we look at these three, we see there's a little bit of something. Let's look at the x-axis. There's a little bit of something. And when you zoom in, as you zoom in, you say, okay, well, here's where that data is smooth. All these other jumps and zigzags, that's just a phone bouncing or zigzagging, picking up micro motions and translating them into the data. So you see there's some movement here, and maybe that's it, but remember, this is the positive x direction, positive y direction, positive z direction coming out of the phone. So the x direction is not how I drop the phone. Let's go back. So when you click on these double arrows here, it says, do you want to keep the selected or do you want to reset the default? We want to go ahead and keep this as selected because we have zoomed in for comparison. So let's keep as selected, click OK, and you can see your screen has been adjusted to show this data on this scale, but it's in the negative x direction. Okay, so let's look at y. Again, we believe that we dropped this along the z-axis, so we're going to look for evidence there, but when we zoom in, there is a little something happening along the y-axis, and it seems to mirror what we saw on the x-axis, just this data, but look, it's only 1 meter per second squared that it picked up, so we don't really want to believe that too much either. Again, we're going to go out, keep as selected, click OK, and now you see these two are kind of aligned, and we could play with it a little bit to get it aligned, but they're showing you that the period of time between 2 and 2.5 seconds for that fall. So let's look at the z-hat. We zoom in and you see there's a very high, by comparison to the other two, there's a very high range of constant data, and if you notice, once you zoom in, you get close to, it scales at minus 10 meters per second squared, which you can play with it a little bit more and demonstrate that your acceleration was showing between negative 8 and 10 meters per second squared, which, if we know, 9.8 is in that range. Why does this have this small amount of decrease in the acceleration due to gravity? Did it actually slow down? It was just falling, or is there some other factor at play? We always want to ask ourselves, why are we getting the data that we get? What may have been happening is your phone is, as it falls, instead of falling straight down, maybe it started to fall along one of the angles, and so your other sensors were picking that up. Once you've got this zoomed in the way that demonstrates you're about negative 9 meters per second squared, and you can demonstrate that if you go to more tools. If we pick data and we pick a point on here, we see that it's negative 9.15. That's good enough data to demonstrate that you're at negative 9 meters per second, 9.8 meters per second squared. Close this, click Keep as Selected, click OK. Now we see you can print the screen, transfer it from your phone, and then use any number of ways to reverse the colors so that you're not using up pounds and pounds of ink. Make sure you show what way the phone was falling, which axis you used to drop it.
Also in this lab, you're going to be introduced to an idea which is called statistical analysis. In physics and in science in general, anytime that you make a measurement and want to report on that measurement, you need to give it context. You need to give it some kind of scientific validity. Just saying that looks good isn't enough. We have to have a way of categorizing and qualifying why something is good and why it may not be good. So we have two different ways to do that here in physics that you'll be using. These two statistical standards are going to be used by you throughout this term and next term, and they represent pretty much the simplest way that you can do a statistical analysis of your data. We're not going to go further than that. We're not going to get into 1 sigma, 2 sigma, or any of the other business. We're just going to look at how do our values stack up either against themselves or against some reference point. So let's start with the first type. The first way that you'll be using in this lab will be percent error. Now, percent error assumes that you know some accepted known value that has been tested, tried and true years and years and is known to be a well understood value. In this particular lab, that value is acceleration due to gravity. 9.8065 is the accepted value. There's a few extra decimal places, but we're going to truncate it at 9.8065 for this lab. So that will be your accepted value here. This expression says take your experimental value, subtract the accepted value, 9.8 meters per second squared, divided that difference by the accepted value, 9.8065, and then multiply times 100 to give you a percentage value. What percentage of the accepted value, 9.8065, is your experimental value? Obviously, for this particular value, you want that closest to 0. You should never accept a true 0 value because it means that something has been overlooked or you're not using high enough precision to make your measurement and therefore to make your analysis. So if you get 0, it's time to dig just a little bit deeper. But what you'll notice in this one is that the reference point here for your comparison, you're making a comparison to some accepted value. We know that acceleration due to gravity is 9.8065. This has been measured with highly precise instruments and been known for centuries. The reason that I've written it in this format is because in Excel, it's a little bit easier to write your calculation, or at least makes a little bit more computational sense, if you multiply 100 times this. And we'll get into the Excel type up in the lab. We won't do this in the video, but just in the lab on how to enter this into your Excel spreadsheet. But for now, suffice it to say that we need a reference point. The reference point here is 9.8065, the accepted value of acceleration due to gravity. By contrast, some of your values are measured and they're different from each other. And in some cases, especially in the upcoming lab, you'll be making measurements of things that don't have an accepted value because they're random or arbitrary measurements. Therefore, the question is, what do we compare them to in that case? And the answer is compare them to the other data points within that experiment. If you do so, you're creating at least a reference point because now you're looking at the standard being something to do with the experimental setup itself. And to do that, you will say percent difference is 100 times. Now we're going to take the difference between two experimental values, and then we're going to divide that by the average of those two values. 1 plus 2 divided by 2. If you think about this, in this case you have the average of the two values. What's the average of the two values? It's going to be some midpoint exactly between those two values. So your reference point is the average of those two measured values. Again, in this case, it really just speaks to what your experimental setup is doing. And just for a little bit of extra conceptual comparison, I drew a couple of images here to help illustrate what the difference between these two calculations are. So here we assume that some measurement has a true accepted value, whether it's an accepted value that's universal true, like acceleration due to gravity on the surface of the Earth. So there's some accepted true value, and you make 5 measurements of that value. 1, 2, 3, 4, 5. 4 of them are grouped together just shy of one side, and the other one is on the opposite side. And you'll notice that they're all compared to this true value would be the percent error. Alternately, so you make those same 5 measurements, but now you don't know anything about the true accepted value. But if you take the average of those values, that becomes your reference point, and then you can take the percent difference between each of those measurements and the average of those accepted values. And this is something that you'll do a little bit later in the term, later in the term, for this lab. And this will be something that you do later in the term a little bit more comprehensively. But for this lab, just go ahead and do it once to compare the average acceleration for the small picket fence versus the large picket fence, just to confirm whether or not the mass made a difference. For these two terms with physics, your threshold, what do we count as good data or not so good data, is 5%. When a measurement is below 5%, whether it's percent error or it's percent difference, when it's below 5%, any anomalous contributors to your measurement that may make it better or worse are negligible enough that you can accept the value as viable, as reasonable, as a useful, acceptable value. When it goes above 5%, it's not automatically this is bad data, but you now have to start asking yourself what contributed to that percent difference being higher than 5%. Once you get above 20%, that's where you go, okay, this measurement is compromised somehow, so that's when you start digging deeper. And this is something you talk about in your analysis section. You highlight it in results section, talk about it in analysis section. And then if you see some systemic issue in analysis, when you're in the discussion section, use that to guide you, saying, here's what went wrong with the experimental apparatus, the experimental setup, and what needs to be done to improve it. Yes, you're going to compare each individual measurement, the slope from your plotted lines, to 9.8 and write down and record what that percent error is for each of those. Then you will compare average value of those measurements and compare the small one to the large one and see how those compare to doing the same comparison with the masses of those two picket fences, and use that to confirm is acceleration due to gravity dependent or independent of how massive it is. But more to the point at the moment is that you will take those two values and plug them into this expression and see how they compare to each other. You dropped two different objects with a photo gate, and you'll be able to use this calculation to make a comment about how well you were able to achieve that goal. Were they within agreement with each other? That, combined with the fact that the slopes are in some agreement with the actual accepted value of 9.8065, gives you a starting point to talk about whether or not, first, were the measurements valid, but also whether or not the experiment was valid. Was the experiment a viable way to make an observation of the acceleration due to gravity and come away with a viable answer? In order to do this lab, you need a PASCO photo gate. We'll take a closer look at that in a moment. 2 picket fences, something to catch them with, a nice soft landing for the picket fences to land, and then our wonderful PASCO setup. The photo gate is a simple sensor which beam of light travels from one side to the other along a straight path, and anytime you block that, you find that the red light flashes on, indicating that it has triggered a stop, or at least that it's blocked. For example, what you will drop are these picket fences. These picket fences consist of dark bands with open space where light can pass through. These trigger the start and stop of the timer for the data collection that we've set up in the Capstone software. You'll notice that even though they are different weights, this is heavier than this one, that they have the same spacing, so they'll do the same triggering of the system with the photo gate. You'll notice that the heavier one does have an extra one, so you will have an extra data point for that set of data to evaluate. To start out, you connect your photo gate, unfurl it. We're going to connect it to the 850 sensor as we did with the previous one, only in a different location. This is a stereo cord pickup. Once you're in Capstone and you're ready to start collecting data, what you're going to do is you go over to the hardware setup, capture that, comes open, and then you'll click on the first tab, go to PhotoGate. As you're going to see, it's going to create a new option here on the left. So you click on the timer, go through the pre-configured timer setup as you see in the lab manual. So it's going to ask you if you want to build your own. Nope, just create a pre-configured. PhotoGate channel 1 should automatically come up. Click on next. Select the type of timer you'd like to create. Click on that timer. You got a few different PhotoGate options. The bottom one is picket fence, so click on picket fence. Select the measurements that'll be done through this one. In this case, you want to add block to block times, but you want to keep speed, acceleration, and position. Next, configure parameters. The spacing between the start of each block on the picket fence is 5 centimeters or 0.05 meters, so you leave that in place. Click on next. That's going to say give the timer a name. You can just leave it picket fence. Once you hit finish, it'll refresh that information. The buttons will look a little weird. It's already been saved. You can play with it for a minute or so if you want to, but it's nothing extra. So you can close that panel by tapping on timer setup again. And now you want to go ahead and put your displays onto the screen. So just bring your graph onto this board, and you can bring over a table if you want, just to kind of see the data come into place if you want. As a matter of fact, I want to do that for those of you who like to see it happen. So I'm going to just slide that right over here, and now you can see it's filling in the space. We need to put over here on the left side block event times, and over here we'll put speed. Over here we'll put time on the horizontal. You notice that we're using time under the time setting, not one of the picket fence time listings there. So this is the derived data that you're going to be working with in Excel later. And then the vertical, you can go with just speed. You can do acceleration, you can do position versus time. Each thing is going to show you a different plot. What we need to see is little simple straight lines. So for now, we're going to keep it as speed versus time. The acceleration is going to come from the slope of the data, and we're going to repeat that in Excel here shortly. But first, I want you to get the data. If we do it as acceleration versus time, it's going to be flat data. It doesn't stand out as dynamic information, and so it may not be as captivating. Even in the subtle bit of being physics, it's not going to be as intriguing, even though it will go directly to the 9.8 value. But we'll swing back to that again in Excel. So here you have the setup. You have the PhotoGate, you have the PASCO setup, you have the two picket fences. One is small and light, the other is a little bit heavier. You'll measure the masses of these just to, for comparison. And a clothespin to drop the picket fence through the PhotoGate in the most cleanest way to drop it. It's an imperfect dropping process when you drop it with your fingertips, so it's a little bit better if you use the clothespin instead. So we're just going to go ahead and set this up. This is ready to take data. You'll notice at the bottom you have record and your control panel down at the bottom. So the way that this is set up, that even though the timer is going, this is only going to take data when the light is broken there. This is now garbage data, so I'm going to stop that, and then I'm going to just start a new run. Don't throw away any data unless you know it's absolutely useless. Even if it seems like it's useless, probably a good idea just to keep it, because you can just not include it in your reports. So you take one of your picket fences, clamp it, try and get as close to the center as you can, just kind of have it there. Now you'll notice if you drop it this way, where you have, if you'll see in the picture here, I'm dropping it where the laser beam is going this direction. This is not going to do a great job of blocking that. So we want to turn it sideways so that falls in between and does an effective job. As you can see, it's now collecting data. It's hidden behind the image on the screen here, but you can still see what's happening here, that this is collecting data. So once again, I'm going to stop this, and we want to drop it, and you want to take it a couple times, make sure that as it falls straight through, it doesn't touch the side of this, doesn't bump into this, land funny, it doesn't twist and turn as it's falling. You want to try and have it as close to center, and then you just tell your partner ready to go. You do that. You can just drop it, go ahead and pick it up, and immediately do it again. Do 3 runs so that you can take an average of these and do the statistical analysis. 2. Now you can take your data and analyze it in Excel. Let's go over how to export that though. So now you have your data. You can do some preliminary analysis here in Capstone, and the way to do that is just come up here, click on this little yellow highlighter. It opens up a box, and you want to change the size of the box so that it covers only one set of the data, like so. And you'll notice that the data that's inclusive is highlighted with a little yellow highlighting around it. And we're going to go up to the red line with the blue dots. This is the curve fitting. We're going to say, I think this is a line. Tell me what that line looks like. And when we click on linear MT plus B, you'll see that now there's a box here, 9.75 plus or minus extra details, but the 9.75, that's close to 9.8. That's kind of what we want. And you can just drag this over to the other spot. You see 9.76, and you can see 9.72. So the data at first blush looks pretty good. These data points that are in between, this is not a real data point. This is from the start of the last line and the start of the next line the next time you drop. This completely ghost data. You can ignore that completely when you get your data transported into Excel. But let's go ahead and export it first so that we can do some analysis. And the way we do that, first you always want to save your data, so hit save, and it'll go into a Capstone file. Keep in mind that your data should also have the data for both sizes, so you want to make sure you have both sets of 3 drops for both the large and the small picket fence before you export your data. The question is, how do we export it? Great question, and here's how you do it. We're going to go to File, Export Data. It's going to pop up a big screen. We want to have the speed, the acceleration, position. There's going to be a lot of data that comes out, and our job is to be parsing through it. So we're going to export the time. Do not need to add anything to this. Date and time is just extra useless information. It's like true stamp time, so ignore that completely. But we're going to keep everything here because we got to process it in Excel. So then we go up to what's the export format. In this case, comma separated values is the most convenient format. You can use tab delimited values. That's messier, and I'm just not familiar with GPX or KML formats. So comma separated values is what it should be. It should automatically preset to that. And we click on export file. It's going to ask you where to put it. So I'm going to go put it into, I'll put that file there. Capstone data, save. Once it's been exported, you can go ahead and close the file. You can exit out of Capstone altogether and go to your own device and pull this up to modify this either in Excel or in whatever other software you're using. So. All right, so now we're in Excel. In the same file, I had a quick start where I just demonstrated running my fingers through the thing. Then I stopped it. Then I restarted it, and I did a couple of movements of the picket fence through there, and that was a separate set of data. And then I stopped it, and I started a third time, and that's what this third set of data is here. So you got the first time where I did junky stuff, second time where I did junky stuff, and then the third time that was the run that took data that I needed. Now, my best policy to advise you anytime you work with data is keep all your data somehow or another. So first thing we got to do, let's save this as an Excel file. So you come into the pop-up, it's going to come down to an Excel workbook is one of your options, and I'm just going to rename this acceleration due to gravity. Save that. Now it's an Excel file. If you try and do anything while it's a .csv file, the system is going to freak out and Excel will get real mad at you. The best thing you can do is just go ahead and save it immediately as an Excel workbook and then begin working. So this is the raw data. So I'm going to come down to the bottom, double click, right click rather, go up to rename. This is Excel due to G raw. Now this is the raw data. This is a work page that I'm not going to make any changes to. What I will do is create a second one. So you click on the little plus, this creates a second file. Since I know that this is not good, full, and the same thing is true for the second set of data, when you click on one of these, you'll see run number 2. run number 1, run number 2, run number 3. We want to keep run number 3, so I'm going to highlight this whole set of data, copy, don't cut, and then come over here and just paste it in place. A little bit of formatting will come a long way, and there you go. Now you've got all the data in one spot that you need to look at. If at any time this stuff is a little bit odd to you and you want to slow it down, obviously you can just push pause. But you can also take a look at how to use Excel as shown in the lab reference tools, because I do have a supplementary one that works with a different set of data in there. We'll call this My Data, and then we'll call it V speed versus time. Good. We'll do it that way. So now that you have the data in one page in your workbook, the way to do this is to go ahead and start taking only the data that you need. We only need to look at, for your first 2 graphs, you only need to have a graph of velocity versus time, and that in here is speed. So we need the time content, copy, which you can Control C, copy, to come over to like column J, let's say you'll do that, and Control V. Time is there. You've just copied it, it hasn't changed it. Then you go to column D for speed, Control copy, Control C, Control V again, or I think it's Command V in Macintosh environment. And all of your speed and stuff is there. Now, the easiest thing you can do, and I will accept this is the first week. This is a lot to absorb already. So this is the first week, and I will accept you doing what I'm about to show you. You can highlight your entire column, go to Insert, and drop down, go over to Charts, click on the little bottom list down at the bottom, which is XY scatter plot. We'll just scatter nowadays. So scatter plot, and then come down and click on this. Now, this may be the only option available to some of you if you're using the Excel browser, which is one of the most useless versions of an advanced program that I've encountered in recent years. It doesn't give you a lot of options at all. You cannot put multiple graphs on there. If you can at all possible avoid using that, I would recommend go ahead and just download, if you can't get access to full Excel, the full Office Suite proper, I would use the OpenOffice.org. I would use the OpenOffice program suite. It's very similar. The learning curve is very low, very straightforward. It is a nice migration from what you may understand from Excel. And there is a tutorial on lab reference tools that you can take a look at, about 12 to 15 minutes. Covers most everything that you need to be able to do in that environment, but it'll give you the option to be able to have all the bells and whistles. So please try to avoid just using the Excel browser. It's not helpful in this environment. So you have these 3 items here now. This is one set of data. If you tried to add a trend line here, you could. And one thing that I'm just going to show you a quick trick right now that you probably saw already. You can go ahead and put most of your place. If you come up to the upper left corner of quick layout under chart design, quick layout, and take the first option. It just has most everything that you need. A little bit of formatting from there is helpful. Probably don't want to eliminate the legend. You make your graph a little bit bigger, and you can resize things, not just in this environment, but when you paste it into your word processor, you can resize it there to make it better fit there, especially if it's Excel going into Word, because they're part and parcel to each other. If you're doing all this in Google, that's fine too. Again, most everything, you probably already know where most everything is if you're using Google as it is. Make the size different. You want to stretch out the graph to fill in the space. We want to take advantage of the space. We want to have as little white space in a presentation as possible. It's a waste of space, and it's poor formatting. It makes it hard to read, hard to grade too. So this is the easiest thing that you can do. Only problem is that if you right click and try to add a trend line, it's going to be a trend line that covers the entire data set, including these garbage data that we already know is garbage. So there's going to be a couple things that we want to do in there to break it up. So let's go take care of that right now. First things first, notice that you have, if you hover over these ghost data, you see the 7.2 seconds, and then over here at 16.152 seconds. Those are the two that we can eliminate. Now, it's removing it for the purposes of analysis. We're not removing it because we're trying to be sneaky with the data. So by removing those here, we're making it easier for us to demonstrate the true data. You want to make sure that you're careful about what data you include and what data you don't include. In this case, I think we can agree that this being a point representing two different drops is dismissible data. So let's go over here. And here's your first data point. So if we delete that, it disappears, and you saw that the trend line changed. And if you scroll down a little bit, you'll see there it is, 16.152 seconds, so we'll delete that as well. The problem, though, is that we still have one data. You may recall that when I chose a type of chart, and here's a chart design, let's click on that. There's change chart type. I clicked that it would be connected data. The reason that the data is not connected is because there are null values, zero values here in between viable data. We don't actually need any of those data points because there's nothing in there. So here's a couple things that we're going to do. First, we're going to highlight this little subsection. And if you go up to data and sort, this data can be separated, and we'll do this under speed. And it's going to do from smallest to largest value in there. If you click OK, now you see that all the zero values are out, and since these are all continuous, then there's something for the data to connect to, and so the dots are connected. Second thing is, even if I do the same thing with the second subset, change this to speed, column K, click OK. It's connected that, but it hasn't affected. You notice that the trend line has not affected. It's still considering this all one set of data. Do the same thing for the third set, and no surprise, again, we have three connected data sets and so forth. So what we want to do is actually add each of these subsets of data in as its own little set of data. That way, we can analyze them with their own trend lines and have accurate representations of the work. So here's what we do. Right-click somewhere within your chart, go down to Select Data. Now we're going to, you see how it says Speed Run 3. We're going to edit this one, and let's change the name. We're going to call this Drop 1, small. And then we're going to come down to Series X. And when we click on this, you see how it's got all these data points along the J column. We only need that first 6 data points. That's all that we're looking for that first drop. So we drop that, and now look at your screen. You saw that it completely dropped away all the other data. Don't worry, we're going to add those back in. They're going to show right back up. Here, we add the K values for the Y. Now, it has all the X data, all the Y data for the first drop. And you notice that this is now labeled here as Drop 1 Small. So next, we're going to add, so in this one, we'll call this Drop 2 Small, and then change our X values. We come down to here, close that arrow, go to the series Y values, highlight just the living data there. Boom, there it is. Click OK. Add one more because we have a third set of data, Drop 3. Click on the X values, scroll down to that X value subset, Y, OK, OK. You have 1, 2, 3 in your list. Click OK and scroll up. And so now you can see all three are connected. You see I've moved the legend a little bit. They are not perfectly vertical. They seem perfectly vertical. And if you right click on each of those, right click, go down to Format Trend Line. But there it is. And when we display the equation on the chart, show the R squared value on this chart, and then just shift this around, and we can see, okay, 9.756. Do the same thing, right click on this data, add a trend line, add equation, display R squared, move that so that's positioned over top of that, and then we're going to add a third one. So we'll right click on this, add trend line, display equation. You'll notice that preset automatically goes to linear. In this case, that works just fine. And we move that here. And last but not least, just a little bit of formatting. Let's stretch this out a little bit and squeeze it so that it fits a little bit better. Just takes a little bit of playing with. There it goes. You can format it to make it look nice the way that you're satisfied with. I'm going to make that a solid line that goes all the way around. Now when I move that out of the way, I've got a black box all the way around. Axis title, this one is, double click on there, velocity, meters per second. Come down to the axis title. Time, don't forget your units. This graph is ready to go. You can add a title here. Click on the plus and go down to chart title. And let's call this small picket fence. This graph is ready to be copied and pasted right into the Word document, and then you can start commenting on it. Now, one of the things that you also have to take into account is the statistical details. The R squared is the goodness of the data, how good does it fit. These are really close to 1. That means the data is very close to agreeing with the type of equation that we picked out. We picked out a line, a linear, and so the fact that these are really close and there's no other evidence that suggests that it should be different or that we have a badly errant data point suggests that these are really good. Now that you've done this, you can repeat for the same process for your large picket fence and have those 2 graphs ready to go. Their values you're going to want to extract and put into a table. Just come over here to the right hand side and just type table of accelerations. You have a small, large, and you have drop 1, drop 2, drop 3, and drop 1 is 9.7561, drop 2 9.7571, and 9.7408. Your table, you'll put those values in there, and then you can do a percent difference calculation. Down in this one, you can follow the instructions in the lab. I'll also talk about this during the lab. And then you'll do a percent error. So that sums up today's lab. Hopefully this was a little bit helpful to you to get the process going a little bit more efficiently for you, and you'll be able to come in and drop things efficiently and analyze them like a scientist. We'll see you next time. You have blah, 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 blah.
Ready?
Yep, 3, 2, 1. Oh, that's okay. That's why we have takes. And go. Hopefully you've enjoyed this video. That's just a terrible amateur thing to say, isn't it? Thanks, James. All right. Well, so one more try. Keep looking at the camera. I will look at like I'm making eye contact with myself. I don't know what to say. And these are the outtakes.